Hello everyone, my name is Anna Paula Garcia, and this is Lab 4, Circuits for Physics 2212. So a brief introduction, the purpose of this lab was to examine energy and current conservation in electrical circuits by analyzing the behavior of resistors in series and parallel circuits. We will measure in this lab actual current and voltage using multimeters and examine the characteristics of ohmic resistors and capacitors. The results, essentially the predictive values of both the current and the voltage, were very close to the calculated values. So some key ideas that we utilized for the calculations and the conceptual aspects of this lab are the Kirchhoff loop rule, or Kirchhoff's voltage law, conservation of energy, Ohm's law, and the node rule. Assumptions. So for the purpose of this lab, we assume that the resistance from the ammeter in the wire is negligible. Now, onto the experiment. In this experiment, we examined DC and RC circuits to understand energy and current conservation. We constructed a series circuit with batteries and resistors, measured current and voltage, and compared them to theoretical predictions. We then investigated RC circuits by charging and discharging a capacitor, observing voltage changes over time to determine the time constant. And this was a very hands-on experience that enhanced our understanding of circuit behavior and measurement techniques. So for the circuit 1, or experiment 1, circuit 1 consists of a simple series configuration with two 1.5-volt batteries connected to two resistors, 47 ohms and 100 ohms, and two ammeters for measuring current. The ammeters are arranged to read positive values of conventional current, allowing for the direct measurement of current flowing throughout the circuit. This setup enables the observation of current behavior in a series circuit, where the same current flows through all components and facilitates voltage measurements across the resistors. So the expected value using Ohm's law is 0.0204 amps, while the observed value was 0.02 amps. Oh, brief backtrack. Here's a photo of one of our experimental setups. It is the only photo I managed to capture. I completely forgot, so I do apologize for not having more photos of the rest of my lab, which is why I will be describing the experiments a little bit more in depth. So moving on to circuit 2. Circuit 2 involves an RC, a resistor capacitor configuration. It typically includes a capacitor connected in series with a resistor and a voltage source. In this setup, the circuit allows for the observation of the capacitor charging and discharging behavior over time. By measuring voltage across the capacitor and current throughout the resistor, you can analyze the time constant, RC, and the exponential nature of charging and discharging the processes. This circuit helps illustrate key concepts in circuit dynamics and energy storage. And for circuit 2, I created a time versus change in voltage graph. My values are to the left that were recorded during the lab, while my chart is clearly there. As you can see, over time, the change in voltage is decreasing significantly. So possible error. Error in this lab can be attributed to errors in computing the values from the derived equations, errors during the setup of the experiment, worn out batteries that could result in small value differences, but also just human error in general, especially with like setting up the lab. My group particularly had a lot of difficulty kind of translating the lab from being online to in person. So yeah, so please take my calculations and my setup with grace. So now on to our discussion questions. What if you were doing this lab in real life and you use an actual ammeter instead of ideal simulated ammeter? What's different about a real ammeter and how would it have affected circuits you hooked it up to? If you did this lab with real circuit components, access to a virtual circuit, link above, this was taken directly from the assignment page, and see if you determine how it behaved differently from the real ammeter use. So using a real ammeter, which we did in this lab, introduces internal resistance, which can lower current readings and cause measurement errors compared to ideal simulations. This resistance may also affect voltage drops across components, altering overall circuit behavior. In contrast, virtual circuits provide simplified, idealized results without these real-world complications. And for our second and last what if question, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach for charge? Would this prediction happen in real life? Explain if you're completing the lab with real circuit components, use an ammeter to measure how long it takes to charge the capacitor when connect directly to the battery and the ammeter. Discuss why the measured time is different from the predicted time. So again, we did use real physical materials in this lab instead of a virtual model. But in an ideal model, a capacitor connected directly to a battery would charge instantly. However, in reality, the internal resistance of the battery and circuit leads slows the charging process, preventing instantaneous charge. As a result, measured charging times are longer than predicted due to these resistive factors. Thank you so very much for listening to my presentation, and I hope you have a great rest of your day.